And for some strange reason, the architects decided to put tile all the way down the hall so it echoes out nicely. All righty. Before we go on, and this will not affect Jenna in any way, here she is. We are going to draw the Mrs. Bad Crumble number line that you all had in grade 3 going around the ceiling of your room. You all had it, every one of you. Some of you had the same teacher for a couple of years in a row. If that teacher really cared, like in kindergarten, she only showed you like 0 to 10. And then in grade 1, she added like up to 20. And then by the end of grade 5, she had up to 100. And then in grade 6 or 7, she uncovered the other half of the number line, which was all the negatives. And you were like, ah! That's how math goes in Canada. In the rest of the world, they start, hey, here's some numbers. Guess what? They go both directions, and they go a long way. They start that in kindergarten. In Canada, kindergarten, by the end of kindergarten, your math learning outcome is count to 10. After a year in school, 10 months in school, your math job should be to be able to count to 10. And we wonder why we are falling behind the rest of the world in math education. Because after an entire year of school, a year, when you are 6, you should be able to count to 10.
My brother can count to 6. Not 6, 10.
I know.
He's 4.
I know. My son could sing like 5 different countries' national anthems at 2. School has set the bar too low. Anyways, so Mrs. Bad Crumble's number line. Yes? All right. What goes right there in the middle of it?
0.
0. Which, by the way, did not exist until around the year 700. The number 0 is only about 1,400 years old. It was an Indian that invented it, yes. Good job. So, yes. So that is 0. It lives there. What lives on the right of 0?
1.
Let's think bigger. This is not kindergarten. What lives on the entire right side of 0? The positives. Excellent. Which means the numbers get greater. What lives on the left of 0? Negatives. Now, this is the first thing that for some strange reason you guys have trouble with. These numbers are getting smaller. I don't know why that confuses people. I say, would you rather have a penny or would you rather have negative a million? Well, what negative a million? Negative a million is way more than a penny. Who do I ask that question of? Numerous students. More students than I am comfortable saying do not understand how numbers work in math class. Don't be one of those students. Negative 6 is less than negative 5. Okay? Okay. Everyone's cool with that, yes? Now, where does this number line end on the right? It doesn't. What does it go up to? To what? Infinity. Does infinity actually exist? No, because you will never ever get there. Because you can always go one more step. Understand? Okay? It's a bit mind-blowing, but yes, you will never ever get there. What lives down here on the left? Negative infinity. Will you ever get there? No, you will not. Everybody cool? We all understand how the number line works, right? Thank goodness for the number line around the ceiling. We're all good? Okay. I say thank goodness for it, but I still have kids who can't tell me what -3 minus 4 is. -7. And what is -3 minus -4? +1. Excellent. I love teaching honors class because it only takes a few seconds to do those. All right. That was a little one. Please look at this word, real numbers. That is there to delineate all the numbers from -infinity up to +infinity. Please notice I've used the word real. There's a reason for that. There is another whole set of numbers that are imaginary, and they are actually called that. It makes you think of Sesame Street. Just like Big Bird's imaginary friend Snuffleupagus, which they had to make his real life friend so everyone could see him. Snuffleupagus, Big Bird, we're okay here, right? Okay. The imaginary numbers do exist. You will not have anything to do with them until well into university, so don't worry about them. We are only talking about real numbers. You lost your carrot. That's the worst. All right, everybody cool? Okay, so let us begin. The smallest set of numbers. The smallest set are the natural numbers. I wish for you guys all to start counting with me. Are you ready? We're going to count just like we're in Mrs. Bag Crumble's class. Ready? 1, 2, 3, and we all counted that way, yes? Yeah. Okay. These are what we call the counting numbers. And they are natural because all of us, when I said, hey, let's count, we all started counting. What number did we not? We never said 0, even though that's a number. So this is 1, 2, 3, up to what? Where could we stop counting? Never. Infinity, right? Got it? Everybody cool? That's the smallest set. And when I say smallest set, that's kind of silly because it's infinite, isn't it? No, a fish would look like this. With some gills. Just because, for expediency's sake, I don't finish the tail. I mean, technically, I should finish the tail. It should have a dorsal fin. It should have a couple of pectoral fins. Right? But that just takes too long.
You ruined it.
All right. Everybody cool? Those are the natural numbers. Now, next year in IB, they will give this a one-letter abbreviation. But I can't remember what it is. I'll get back to you tomorrow. Okay? The next set, which is the next smallest, are whole numbers. Whole numbers are naturals plus 0. Okay? So it is 0, 1, 2, 3, up to infinity. Is everybody cool? Yeah? Everyone's good? Easy peasy lemon squeezy, correct? Third set, integers, which is getting bigger. Please notice the sets get bigger as we go down the line. Integers are the wholes plus the negatives. So it's -1, -0, 1, up to positive infinity, and down to negative infinity. Is everybody cool there? Everyone's good? And finally, we add the rational numbers. Now, rational numbers I'm going to take a little bit of time with, okay? Your guys' math education for counting went this way. You started out with 1, 2, 3. How old are you? I'm 2 years old. And your mom went, no, honey, you're 2 years old. Back when your mom loved everything you did. When you were around 3, you started to misbehave, like every child. It's called the terrible twos. When I was your age, 2, 3, and I misbehaved, we got spanked. Swatted across the face, backhanded, whatever needed to be done to stop that behavior. You guys grew up in a time when that wasn't allowed. Fortunately for math teachers, your parents counted, many of them. Go clean your room. No. 1? Okay, and you went to clean your room.
Yeah. Exactly.
Yeah? And your mom was like, I'm a good parent. For a couple of months. And then your mom said, go clean your room. And you went, no. And your mom went, 1, 2, and off you went to clean your room. Because you didn't want to get to 3. Because you didn't know what was going to happen. Right? In my day, go clean your room. No. Yeah, I'm cleaning my room. Got it. Don't smear poo on the wall. Got it. Well, you're 2, right? Anyway. You eventually realized your mom and dad would get to 2, and they didn't want to get to 3 because they didn't know what they were allowed to do anymore. 20 years ago, they knew what to do when you got to 3. But now they don't. So you all of a sudden learned, at about the age of 3 or 4, you learned fractions.
Yeah.
Because your mom went 2, and you went, and then she went 2.5. And you went, what the hell's a half? Except you were like 3 years old. She's like, and your mom was like, and you were like, okay. And you went and cleaned your room. Now, if your parents were good with math, how many times could they do that? Infinitely, couldn't they? Because they could go 2 3/4, 2 7/8, 2 9/16, 2 and so on and so on and so on. And would they ever get to 3? No, because you can always cut it in half. If I walk to Emma and I cut the distance in half every time I take a step, will I ever theoretically get to Emma? No. So if your parents were good with fractions, they could count forever. And all of a sudden, 1, 2, 3, your natural numbers, became this. 0, 1, 2, and how much space is there in between? Infinity. And all of a sudden your minds get blown. About grade 3 or 4, when your mom's punishment technique, 1, 2, 2.5, became mathematical theory. Right? And we spent all of kindergarten, all of grade 1, all of grade 2, all of grade 3, counting 1, 2, 3, 4. And then in grade 4, your teacher says, oh, by the way, everything you know about math now applies infinitely between 1 and 2. And that's when fractions were introduced, and that's when you guys went, nah. Because fractions, if you ask anybody, is still the hardest thing to get you guys to deal with. I know this because I'm trying to teach pre-calc 11 right now with some fractions, and every kid, can I use decimals? No. Okay? Everybody with me? All right. So rational numbers, these guys, you know them as fractions. But they're actually so much more rich than that. Here is the real math definition of them. I'm just going to move this off to the side. I know you can't do that, but I can. Oh, I can also make it disappear. Not that I wanted to, but it did. A rational number is this. It is any. Please recognize the word any. Any expression. Oh, we're losing letters. Oh, we lost the I, we lost the X. And we can't turn it off. Any expression written like this. X over Y. Anything that is written like that, except X and Y must be integers, and Y cannot equal 0. If you can write that, you have what we call a rational number. You guys know them as fractions, okay? But they are also decimals, because X over Y means X divided by Y. And that gets you your decimal. Is everybody cool? All right. Now, I'm going to write something in red over here. Rational decimals must repeat or end. And we'll come to that in a moment, okay? Everything that is number over number is a rational number, automatically. But every decimal is not automatically rational. Everybody cool? Okay. Now, if we can have rational numbers, we can have irrational numbers. And irrational numbers are simply these. These are decimals that neither repeat nor terminate. What's the most famous irrational number? Pi. Okay? Now, some of you will say, Mr. Myers, pi is a rational number because pi equals the circumference divided by the diameter, doesn't it? And isn't that X over Y? It is, but these are not integers. Because if you actually take a perfect circle, you will find that this one of these may indeed be an integer. But if your circumference is an integer, then your diameter will end up being a decimal. Is a decimal an integer? No. Everybody cool? So because this is an integer over integer, pi becomes irrational. Everybody good? Okay. All the other irrational numbers that matter to you guys are square roots, square root of x, that is not perfect. Okay? And we saw that already. I've given you the example of that. The easiest one is this. If that side's 1, that side's 1, this side is root 2. Does root 2 have a decimal? No, because when you punch it into your calculator, you get 1.414, and it goes on and on and on. Everybody cool? Easy peasy lemon squeezy. Here's where it gets weird. Is the square root of 12.25. Do you think that is rational or irrational? What do you think? I said any square root of x that isn't perfect. Does that look like it's got a square root? Doesn't look like it, does it? But of course, if you check square root on square root 12.25, you find that it indeed is a perfect square. Everybody with me? So don't be fooled by looks. Everybody cool? Okay. Let's move it along. Turn the page over. Oh, hey, look, there's that number line that disappeared. All of you should be able to do the first one already. How do I convert a decimal to a fraction? This is like grade 6. How do I do that? What? Why is it 100? Yes, this is 12/100ths. So that's a fraction. That's a rational number. What makes it a rational number? There's 3 reasons you could give me right now. Somebody give me one of them. Sam. It ends. 0.12. Stops at the 2. That makes it rational. What else makes it rational? Tavleen. A over B, they're both integers, and B is not 0. Excellent. Cool. What's the third reason that it's rational? Well, that's exactly what Tavleen just said. Okay. The third thing that makes it rational is we can move it around and keep the same value. Because this is really 6 over 50, isn't it? And it's really 3 over 25, isn't it? Right? But it's also 24 over 200. Everybody cool? Those are the 3 reasons that's rational. Everybody good? All right. Now, let's look at B. It says convert it to a fraction, which means, I'm going to give you a hint here, all of these will convert to fractions. Why do you know they'll convert to fractions? Because of what Stanley said here. This one ended. This one, what does that little line mean? It repeats. So this is really 0.11111111 for how long? Forever and ever and ever, to quote my favorite iCarly villain. The girl that takes them hostage in iCarly, I'm going to keep you here forever and ever. And you guys know that one, right? You all watch iCarly, don't lie. iCarly was awesome. You should have watched it. I'm so sad. Because it's awesome. I'm a huge iCarly fan. All right. So, Tavleen, it is indeed 1 over 9. Now, here is why. If it were 0.1, what would it be? What would 0.1 be? 1/10, correct? But this is 0.11111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111111 right? Is that more or less than 0.1? Slightly more, isn't it? Because 0.1, right? If it's going to be a fraction, they have to be integers, don't they? So if this is going to be 1/10, what's the closest integer to 10 that is bigger than tenths? 1/9. So that is why a repeating decimal must go over 9. Is everybody cool? Now, I'm sure many of you had a teacher at some point that said to you, a repeating decimal is over 9. I don't know if they told you why. That is why. Is everybody cool with that? I like to tell you why, because a lot of kids forget that 1/9 is bigger than 1/10. Because 10 is bigger than 9. Same with the negative $1 million or a penny situation. Okay, everybody cool with why? All right. Now I want you to look at C and tell me, how does C differ from B? It's a 2. What else? Close. You don't know that that's repeating, do you? The 10 billionth decimal there might be a 7. Do you understand what I'm saying? This one you know, this one is we are guessing. But if we were to guess, this, our assumption is it is 0.2 repeating, yes? Which would mean it would be what as a fraction? 2 over 9. When it was a 1, the 1 went over 9. When it was a 2, the 2 went over 9. Yes? All right. Now, what is this one really? 0.54. What's the next decimal? 4 for how long? Forever and ever. Okay. So now I put it to you. Some of you will have been taught a trick for this. Some of you won't. Let's logically figure it out. How many digits repeat? 1. I know every repeating digit has to be over what? 9. Everyone agree? Okay. Now, 0.1, I had 1 9 down there. 0.2, I had 1 9 down there. How many digits do I have here? 2. So can I have it over one single 9? No, I can't, can I? I need bigger numbers there. Because if I put 54 over 9, what do I get? 6. That's not 6, is it? So it can't be over 9. So what do I use in math to show a placeholder? 0. Okay, so I have 54 over 90. Everyone cool with that? Is that okay? Okay. Well, isn't that 6/10? So isn't that 0.6? So is 54 over 90 okay? No. So what must I do? Do you think? Let's see. So Priyanka's guess is 54 over 99. Now when we had 1 over 9, we got 1, 1, 1, 1, 1. 2 over 9 got 2, 2, 2, 2, 2. What do you think 54 over 99 will get you? 54, 54, 54, 54. We're getting warmer, right? So this is close, but not quite right. Has anybody been taught this trick? What is it? Over 11? If I had 54 over 11, I would have 4 point something, wouldn't I? Almost 5. So, but you're on the right track. We have to manipulate something. Max?
Could it be over 91?
91. Why do you think 91?
Because, there's a 9 on the bottom, there's also a 1, and the 1 is, maybe it will look, I haven't tried it.
No, of course, yeah, because we're guessing here, right?
Yeah.
We're using logic, okay? We know we have to manipulate these numbers, right? So if we do 91, what do we get? 54 divided by 91. It's getting bigger. So we've manipulated the denominator a few times and it hasn't worked. Where else can we manipulate? Everything we've done to the denominator hasn't really worked. What's the closest we've gotten? 54 over 99 is close. 99 is close. And the other thing we had was 54 divided by 90, which was close. What can we manipulate now? We've tried the denominators. What else should we try? Okay, so 50 over 100 plus 4 over 9. Let's see what that gives us. So we know that's 0.5, yeah? 4 divided by 9 is 4, 4, 4, 4, 4. So I would have 0.5 plus 0.4, 4, 4, and so on, right? So what is that? Doesn't quite work, does it? But I like what you're thinking. Again, you're thinking along the right track. You're splitting it up. Okay. So if I can't add, what could I do? I had 0.5, right? 50 over 100, and 0.4, right? Okay, and that didn't work. Why did you pick 0.5 and 0.4? 1 second, Tavleen. Sonia, why did you pick 0.5 and 0.4? Well, why did you do what? Why did you do this?
Because 5 is in the, it's like 50, and then 4 is in the...
So 5 is 5/10. What's wrong with this? Is this 4/9? It needs to be over 9 because the 4 repeats. But it's not 4/9, is it? Because 4/9 would have been if it was the first decimal place. Isn't that the second decimal place? So what do I need as a placeholder? 4 over 0.9 would be 4 over 9. What could it be? 4 over 90. Now let's check. 5 divided by 10 plus 4 divided by 90. Oh! What did we get? Exactly what we wanted, right? So, if we were going to add these, what's the common denominator? $90. So did this guy change? Nope. So it's plus 4. Did this guy change? What do I do to 5/10 to get it over 90? Multiply by 9. What's 5 times 9? 45. 45 plus 4 is 49 over 90. Now, that we know now through logic is our correct answer, yes? Everyone agrees? Now, in your previous math education, you would have been given the shortcut here, right? I don't like that, because what if you forget the shortcut? Then you're screwed, yes? But if you know how to get there, you can always work it out, right? We started with 54, and we ended up at 49. Look closely and see if you can devise the shortcut that gets me from 54 over 90 to 49 over 90. You took away 5 from what? 54. Okay, now look at the question. What did we start with? 54. What did we take away? 5. Why did we take away 5? Let me give you another one and see if you can put it together. 457 repeating. What would that be as a fraction? Look at what you know and see if you can put it together. What would the denominator be? Can it be just 9? No, why? 3 decimals. So it has to have 3 numbers down here. Can it be 900? 0.54, the 4 repeated, so it was 90. Now I have 0.457. How many are repeating? So it must be 990. Everybody cool? Okay, now what goes in the numerator? Look at what we did here. 457 minus how much? Look at what we did here, because math is a pattern. What did I do with 54, 5, and 49? Tavleen.
Oh, okay, it would be,
4 over 10 plus 57 over
990.
just, okay.
Yeah.
So what would I do?
The common denominator would be 990
Okay,
times the 4 by 99.
by 99. And then I could add them, right?
Yeah.
And that's going to get me 453 when I do that. Okay? So, what can I do up here to get 453? Max?
What I did was I put in I put in 547 minus
457.
Yeah,
Yeah.
and then I subtracted 4.
You
because
subtracted 4.
That is the first number.
Because that's the number that's not repeating.
Yeah, and then
Just like we did here. 54 minus the 5 got me 49. Everybody cool? That's the shortcut. Okay? Every number that repeats gets a 9. Every number that doesn't repeat gets a placeholder. What's the placeholder? 0. The numerator has to be what repeats minus what doesn't repeat. Everybody cool? All right. Now, next thing. We're going to put these into the appropriate category or categories. These are on the first page. And we are going to use our calculators to do this. Okay? I've put the most difficult one first. All of you on your calculator should have a button that has a little 3 with the square root sign. Please look for it. It's probably a shift button, like shift sign, but it isn't necessarily. Has everybody found it? We used it before in our measurement unit, yes? So now to punch this into your calculator, if you have a forward calculator, for me, mine lives in this math button. See? 3 root. If you have this fancy calculator, you got to hit the math button and you'll get it. Cube root. Now what would I put under here? Negative 14. Everybody cool? You guys, if you have a backwards calculator, you're going to do it the other way around. You're going to punch negative 14, then you're going to hit that cube root button. Got it? And when I hit enter, what do I get? So have a look at that. Did it fill up the screen? Is there a discernible pattern on the screen? No. Is there discernible repetition on the screen? No. What do you think happens at the next? Why does this end? Because the screen ends, right? So this is, it's got a root sign and it's not perfect. So what category does it belong to? It is irrational. Why? Phil's calc screen. Phil's calc screen and no pattern. Now, if my calculator screen went out to infinity, do you think that this will start repeating? Or ending? No, it will not. Everybody with me? All right, let's look at this one. You don't need your calculator for this. What's the square root of 25? 5. What categories does the number 5 fit into? Is it a natural number? Do we hit it when we count? Right, we do. So it's natural. If it is natural, that automatically makes it what? Whole. That automatically makes it what? Integer. And that automatically makes it what? Rational. Everybody cool? Okay, now C, half of you are going to get wrong. What is C? Everybody write down what C is. Does it have a pattern? Does it repeat? Does it end? Yeah. So this is rational. Why? Because it ends. This is 5 319,754,000 millionths. Understand? Everybody cool with why this one's rational? It's because it ends. What's this one? You knew how to do this in grade 9. This level of exponent was taught to you in grade 9. What's the answer here? Positive 16. What groups does that fit into? Natural. Once I write natural, does that automatically cover everything else? Yes. Everybody cool? What about 9? Natural. What about F? What's the square root of negative 4? Can't do it. Why? Can't have a negative square root, can you? Because negative 2 times negative 2 is what? Positive 4. 2 times 2 is what? Positive 4. To get negative 4, I'd have to use negative 2 and positive 2, wouldn't I? And a square root, they have to both be the same, yes? This is your imaginary numbers. The square roots of negatives. They only exist in theory. The higher you go in math, the more you'll see them. And there's a fun math joke for math nerds. It's this. Square root of negative 1 is looking at pi. And square root of negative 1 says, be rational. And pi says, get real. Math jokes are funny. Get it? Because pi isn't rational and the square root of negative 1 isn't real. Here's another one. Square root of negative 1, 2 cubed, this symbol, which you know from Excel if you have done any square rooting, and that. Does anybody know what that says in English? The square root of negative 1 is imaginary, so it's I. 2 cubed is what? 8. That symbol is a Greek symbol for sigma, which means sum. Pi. Did I do that one already? Damn. I ate some pie. Yeah, Mr. Keeley has the shirt. All right, now look at G and tell me what is G? What? I'm hearing both. Which is it? You don't know, do you? How does this appear? It appears as what? It appears rational. Why? Because 1, 8, 1, 8, 1, 8, 1, 8. It appears rational. What might happen at the 9,000th decimal place? There might be a 7. Understand? It appears rational, but we can't be sure. Is everybody cool? Okay? All right. Now, if you turn your page over in your books, you will see an assignment on this stuff. Don't do that yet, because it will literally take you 2 seconds. Okay? Actually, we're out of time, aren't we? Okay. So yeah, do that. That's your homework tonight. It's unbelievably easy. When is it due? Woden's Day. Wednesday, because you're writing a test tomorrow. Oh, wait, what's happening on Woden's Day? Field trip, my favorite one of the year. Huh? You're all going. No.
What if I get injured on the bus?
No.
Do I get to sue?
No. Attendance is to be taken on the bus.
For Monday, April 3rd.
So you are doing, what page is that in your book? Page 101? 97. That's your homework? It's not due until Thursday.
201. Abby's Got Talent auditions start today. If you signed up for a time, go to stage and have lunch as soon as you can. Green team, maybe today, lunch, Mr. Morrison.
Your cumulative.
Wednesday lunch, A206.
We'll talk about your cumulative. Talk about it tomorrow before your test on trig.
There's an important B-Day meeting at lunch prior to the meeting to all participants must attend. On Thursday afternoon, the 13th, a little over a week away, Amanda Lindfeld will be at Abbey. She's a journalist from the Calgary Herald who was captured and held in Somalia after 15 months. Hers is a story of overcoming trauma through resilience and forgiveness. The event is open to grade 10, 11, and 12 students with teachers' permission. Every person going to the event needs a ticket, however. Look for posters in the hallway and talk to your Block C and D teachers. More information,